So we've seen that how charged each of the particles is affects how strongly they attract or repel one another. In this investigation, we're going to explore this more. We're going to keep each of our pairs of charges at a distance of 4 meters apart. We're going to keep Q2 at 200 times 10 to the power minus 6 coulombs, and we are going to change the magnitude of charge 1, as you can see with the slider being moved further and further to the right in successive readings. So that's what we're going to do in this investigation. So if that is what we're going to do, what is the question that we are researching? What is the independent variable? What are we making different between the treatments? And what is the dependent variable? What are we going to measure as an outcome? How does charge 1, or you could say the magnitude of charge 1, Q1, affect the force between two charges? To be exact, the magnitude of the force between two charges. So we're going to vary what charge 1's magnitude is. And then we're going to see in each case what is the resultant force, the magnitude of the force between the two charges. So what must be controlled to make this a fair test? We're going to keep charge 2's value constant, and we're going to keep the distance between the two charges constant between the treatments. And that could be any value, but what I've chosen in this particular investigation is I'm keeping charge 2's value at 200 times 10 to the power minus 6 coulombs. And the distance between the two charges is going to be maintained at 4 meters. The distance is measured from the centers of each of the charges. So let's prepare a table so that we're ready to put our data in as we open the simulation and we work with it. Our question is, how does the magnitude of charge 1, Q1, affect the magnitude of the force between the two charges? So what is the heading of our table? And what is the heading of each of the columns in our table? Pause until you've decided that. Table showing the relationship between charge 1, or we could say between the magnitude of charge 1, Q1, and the force between the two charges. Or we could say, and the magnitude of the force between the two charges. If we leave off magnitude, it's because we imply it. We assume it's obvious. But make sure that you do understand that we're speaking now only about magnitudes. So our independent variable is the magnitude of charge 1, Q1. So that is our heading of the first column, and its unit is coulombs, C. Our dependent variable is the magnitude of the force between the two charges. So that goes into the second column's heading, and the unit is newtons, N. So we open up our simulation. The magnitude of charge 2 is set at 200 times 10 to the power minus 6 coulombs. The distance between the charges set at 4 meters. Now I systematically vary the magnitude of charge 1, and each time I take the reading of the force associated with that Q1 magnitude. First reading, Q1 equals 6 times 10 to the power minus 6 coulombs. Force 0,7 newtons. I increase Q1 to 10 times 10 to the power minus 6 coulombs. The force also increases to 1,2 newtons. Q1 14 times 10 to the power minus 6 coulombs. Force increases to 1,7 newtons. Q1 18 times 10 to the power minus 6 coulombs, force 2,2 newtons. Q1 22 times 10 to the power minus 6 coulombs, force 2,7 newtons. Q1 26 times 10 to the power minus 6 coulombs, force 3,2 newtons. 30 times 10 to the power minus 6 coulombs, force 3,7 newtons. 34 times 10 to the power minus 6 coulombs, 4,2 newtons. 38 times 10 to the power minus 6 coulombs, 4,6 newtons. 42 times 10 to the power minus 6 coulombs, 5,1 newtons. 46 times 10 to the power minus 6 coulombs, 5,6 newtons. And our last reading, 50 times 10 to the power minus 6 coulombs, and we get the highest reading from the set, 6,1 newtons. We put all of that into our table. And what do we notice? The most obvious thing is that as we increase Q1's value, the force between the two charges also increases. So the more, the more. But is this direct proportion? Is it the more by the same factor? Now remember to check whether two variables are indeed directly proportional to one another. A very easy thing we can do is simply divide one by the other, and if the variables are are directly proportional to one another, that will give a constant value. For example, in the data given here, when we divide the independent variable by its associated dependent variable, we always get 5, which happens to be the k, the constant value for this set of data. So will we find the same kind of effect with this data? Is force directly proportional to Q1? To check that, let us divide force by Q1. 0,7 divided by 6 times 10 to the power minus 6. 1,2 divided by 10 times 10 to the power minus 6, and so on. Make sure you know how to use your calculator correctly. Just to be sure that you do, let me do the third one slowly with you. 1.7 divided by 14 times 10 to the power minus 6 equals. You do the same kind of process for all of these numbers. Pause the movie until you've done this. And we find that indeed we do get a constant value when we divide force by Q1. What would the unit of force divided by Q1 be? Force is measured in newtons and Q1's value is in coulombs. So force divided by Q is newton per coulomb. And in fact, this value is a specific variable called electric field strength. Force divided by charge, force per unit charge, is equal to electric field strength. So these are the electric field strengths which Q1 experiences from Q2. Since Q2 is controlled, the electric field strength that Q1 experiences from Q2 is constant. It's independent of the value of Q1 because it's the force per every coulomb of Q1 that Q1 experiences from Q2. Remember, the whole reason why we checked whether we get a constant value here is that if we would get a constant value, that would show us that the two variables are directly proportional. So from this we can see that indeed they are directly proportional to one another. As one is increased, the other increases by the same factor. Here we can represent in symbols and units the relationship between electric field strength, force and charge. Electric field strength equals force per charge. Newtons per coulomb is equal to newtons divided by coulomb. If we plot this data on a graph, we get a straight line. If we would extend the line to the origin, it would indeed cut through the origin. And this is another way that we can see that these two variables are indeed directly proportional to one another. Pause the movie while you complete the labels of the heading and the axes. This is a graph showing the effect of charge 1, or the magnitude of charge 1, if you like, Q1, on the force between the charges, or on the magnitude of the force between the charges. Our independent variable is the magnitude of charge 1, Q1, measured in coulombs. Our dependent variable is the magnitude of the force between the charges, measured in newtons. Let's calculate the gradient of this graph. Gradient is rise over run. Rise is the change in the y value. The y-axis in this case is force. So the rise is the change in the force, the difference in force between our highest and our lowest readings. The run is the change in the x value readings. X in this case is Q1. So the run is the difference in charge values, charge magnitudes, between our highest and lowest readings. So the rise is 6,1 minus 0,7 newtons. So the difference in our highest and lowest Newton readings for this set of data was 5,4 newtons. The run is 50 times 10 to the power minus 6, which was the strongest charge magnitude for Q1 that we used in this data, minus 6 times 10 to the power minus 6, which was the lowest value of Q1 that we had in this data. The difference between those two values is 44 times 10 to the power minus 6 unit coulombs. 5,4 newtons per 44 times 10 to the power minus 6 coulombs is equal to 1,2 times 10 to the power 5 newtons per coulomb. It's the same value that we got in our table. So the gradient of the graph of force against the charge of Q1, as long as Q2 is controlled, gives us the electric field strength that Q2 exerts on Q1. So what is our conclusion for this investigation? The question we were asking is, how does the charge, magnitude of the charge of Q1, affect the magnitude of the force between the two charges? What is the answer to this question? We've seen that the two are directly proportional to one another. How should we word this? It's important to get the independent and dependent variables the right way around. And if we word it in this format given here, you must name the dependent variable first and the independent variable last. The force between two charges is directly proportional to charge 1, Q1. Or more exactly, the magnitude of the force between two charges is directly proportional to the magnitude of charge 1, Q1.